Welcome back to the deep dive. So, just a few short years ago, the entire tech world was completely captivated by the sheer, just colossal power of that first wave of generative AI.
Oh, absolutely. We're talking about the GPT-4s, the massive Gemini models.
Right, all the proprietary giants that were just dominating the headlines. It really felt like we were living in the era of AI giants.
Mhm. And the thinking was, if you didn't have hundreds of billions or even trillions of parameters, you just weren't really in the game.
You weren't playing, it was a race for size.
It really was. And the results, I mean, they were incredible in terms of raw capability. But that size, it came with this trio of huge drawbacks that we've now seen just cripple enterprise adoption.
Okay, so what were they?
Well, first, the literal cost. The computational cost of running these things at scale was prohibitively expensive for most companies.
And I imagine the energy use was massive.
Just enormous. And third, and this is the critical one, a total lack of transparency and, control over your own data.
And that inability to scale affordably, plus all those mounting compliance concerns, that's exactly why something just fundamentally shifted in 2025.
It's a whole new era.
It is. We are now officially entering what our sources are calling the smart scale era. And this is where that old mantra, that size equals superiority, has just been completely debunked.
Yeah, thank you, Mark.
The new frontier isn't about raw parameters anymore. It's about intelligence density. It's all about maximizing performance while at the same time just slashing those inference costs.
And crucially, enhancing control and privacy for the user.
Exactly. So our mission for you today is to really unpack this seismic shift.
We've synthesized a huge stack of source material. We're looking at the top low-cost API models, the new generation of minis and fasts, the leading open source models, and all the tech strategies driving this.
Things like quantization and local deployment.
Right. And we want to show you exactly how companies and developers are now getting access to what is essentially frontier-level capability, but at a tiny fraction of the traditional cost.
Which offers a massive, immediate competitive advantage.
In every single sector.
That sounds absolutely revolutionary, especially for organizations that were just priced out of that first wave.
Okay, let's unpack this and jump right in. Let's talk about the core problem, the economics that made that era of giants so unsustainable.
Well, it really all begins with the limitations of those initial proprietary LLMs. While they're amazing generalists, they can write poetry, they can code.
Summarize ancient texts, you name it.
Right. But their computational needs were just immense. They're resource heavy, they require huge GPU clusters, and for most enterprise use cases, they were simply cost prohibitive at any kind of scale.
This wasn't just an engineering problem then, it was a business model barrier.
It was a fundamental business barrier, and it was rooted in three main enterprise concerns.
And the first one, the one that immediately hits the CFO's desk, have to be cost, that per token pricing model.
It's manageable if you're, a consumer running a few queries here and there.
Sure, for personal use. But when an enterprise scales up to millions of customer interactions, or it's processing huge internal document libraries every single day, that variable cost structure becomes prohibitive. And even worse, it's incredibly unpredictable.
Can you give us an idea of the scale?
Yeah, think about a company processing just 10 million tokens a day, which isn't that much for a large enterprise.
Okay.
With those older frontier models, that could easily run into thousands of dollars every single day.
Wow.
That kind of cost just erodes your margins for tasks that should be commodity processes, like simple data extraction or classification.
And you mentioned unpredictability. That's a killer for budgeting.
It's crippling. How can you commit to a major AI initiative if the price might just double next quarter? It really drove enterprises away from those general-purpose LLMs and towards solutions they could actually control.
Which leads directly into the second and, perhaps the most serious concern, especially for regulated industries, privacy and compliance.
This one is completely non-negotiable for large organizations. Companies in finance, healthcare, government. They're extremely and rightly nervous about sending sensitive, confidential data.
Patient records, proprietary trading strategies.
Exactly. Sending that to a third-party API provider doesn't matter what their security assurances are.
It's just too much of a risk.
It's a huge risk. You risk major data leaks, you create unauthorized data access points, and it instantly complicates compliance with all the major global regulations like GDPR and CCPA.
So the default position has to be privacy by design.
It must be. And that means keeping your data inside your own firewall. Relying on a third party, even one with a stellar reputation, is automatically a strike against compliance.
It introduces all this regulatory overhead that just kills the speed and agility that AI is supposed to give you in the first place.
Precisely. And then there's the third factor, which is flexibility and control. If your core business logic relies entirely on a single vendor's API, you are locked into their ecosystem. You're stuck.
Vendor lock-in.
Total vendor lock-in. You have very limited ability to customize the model's internal behavior or fine-tune it on your own unique domain-specific knowledge. The kind of knowledge that those proprietary models trained only on the public internet just don't have.
So you're essentially renting a generalist's brain when what you really need is a specialist.
That's a perfect way to put it. The whole goal of using AI is to get a competitive advantage. If every single one of your competitors is using the exact same black box API, where's your edge?
There is no edge.
None. So that need for tailoring, combined with the cost, the privacy risk, and the lack of control, that confluence of problems drove the necessary paradigm shift toward what we now call the small language model, or SLM, approach.
The rise of the SLM paradigm it's truly fascinating because it feels like a total reversal of the last 5 years. We used to see a small model as a sign of, technical limitations.
Right, like it was a lesser version.
Exactly.
Yeah.
But now it's a deliberate strategic choice. So how are we defining a small language model in the context of 2025?
Well, the definition is a bit fluid, because the technology moves so fast.
Sure.
But generally, we're defining an SLM today as a streamlined model. It's often trained on fewer than, say, 10 billion parameters, but sometimes it can go up to 50 billion if it's extremely optimized, like one of those MOE variants.
And the classic baseline.
The classic SLM baseline is often models trained on up to about 1 billion parameters.
Okay, let's bring back that analogy our sources use because I think it's so helpful for grasping the difference here.
Oh, yeah, the car analogy. It's perfect. The big LLMs, the GPTs, the full groks, they're the Ferraris. Magnificent, incredibly powerful, consume a massive amount of resources, and you only take them out on special occasions because they cost way too much to run every day.
Right.
The SLMs, on the other hand, they're the Honda Civics.
They like it.
They're reliable, they're extremely efficient, they're accessible, and they absolutely get the job done for 95% of your daily driving tasks.
Yeah.
Your data extraction, your summarization, your classification. They're built for reliability and efficiency, not just raw power.
And the cost differential is, well, that's where the rubber really meets the road.
The efficiency gains are just massive. SLMs offer much faster training times, significantly lower computational requirements during inference, and they're exponentially easier to customize for those highly domain-specific tasks.
And crucially, they're light enough to deploy on consumer hardware.
Or even better, on edge devices. Think about Gemini Nano. It runs directly on a standard smartphone or an IoT device.
So the data processing is happening locally?
It's happening locally, which upholds that privacy-first policy. This is powerful for everything from, advanced autocorrecting on your phone to personalized health monitoring where your data never, ever leaves the device.
And that cost reduction is the core metric driving all of this enterprise adoption. We are talking about lightweight models, often under 8 gigabytes in file size.
Which is tiny in this world.
And they can reduce cloud costs by an immense 70 to 90%.
70 to 90, it's a staggering number. And it's simply by eliminating that variable per token API pricing.
That's revolutionary because it moves AI inference from an operational expense, an OpEx model,
to a predictable capital expense,
Yeah.
CapEx model. You buy the hardware, you run the model, and the inference is essentially free after that. It allows companies to process volumes of data that were just economically impossible before.
So while the open source community was building these efficient models, the proprietary providers, OpenAI, Google, Anthropic, xAI, they didn't just sit still, did they?
Oh, not at all. They recognized that the market was demanding performance per dollar, not just raw performance. So they adapted, and they adapted fiercely.
How so?
They introduced specialized, cost-optimized model variants. These are the mini and fast derivatives we're hearing so much about. They did it to participate in this democratization of AI while, still retaining their market share.
Okay, so let's get into the numbers because they really illustrate the true scale of this cost war. Our sources are indicating that the price to achieve what we used to consider GPT-4 level performance has plummeted.
Plummeted is the right word. It's dropped by roughly 50x per year between 2020 and 2025.
50 times. That's not a gradual decline. That's exponential cost destruction.
It is absolute disruption. This aggressive cost slashing is why we are now talking about models like Grok 4 Fast and GPT-5 Mini. They're achieving near state-of-the-art benchmarks at roughly 1/12 the cost of their older frontier-level predecessors.
So that establishes the new pricing standard.
It does. You now get top-tier reasoning performance for what is essentially near-commodity pricing. And that fundamentally changes the ROI calculation for basically every enterprise AI project out there.
Let's dive into the specifics then, because every major player has a cost-effective API model, and they all seem to have achieved this efficiency in philosophically different ways. We have a great comparative table of the top 5. Let's start with Grok 4 Fast from xAI, because it appears to be the efficiency champion right now.
Grok 4 Fast is definitely the aggressive market entrant. It offers the largest context window on this list, a truly massive 2 million tokens.
2 million? That's huge for any enterprise dealing with, say, long compliance documents or entire code repository.
Oh yeah, or exhaustive conversation histories.
Yeah.
But the pricing is really the headline here. The input price is the lowest on the list at just 0.2 Ethereum per million tokens.
20 cents.
And the output price is also the lowest at 0.50 per million tokens.
That is incredibly aggressive pricing, especially with that vast context window. So how does xAI maintain flagship-level performance at that incredibly low cost?
It all comes down to architectural optimization and how they manage computation internally. Grok 4 Fast is designed to match the performance of the full Grok 4 model.
Okay.
But the key insight is that it manages to do so while using about 40% fewer thinking tokens internally.
Fewer thinking tokens. What does that mean in practice?
It means they've optimized the model's reasoning process, the attention mechanisms, the sparse activations, to be highly selective about which parts of the model it actually needs to engage for any given query.
So it's more efficient.
Way more efficient. Less internal computation means lower latency and massively reduced inference cost. This focused efficiency is what allows it to score so well, hitting 92.0% on the rigorous AME 2025 math and reasoning contest.
So that metric, using 40% fewer thinking tokens, is kind of the new measure of AI quality, efficiency of thought.
That's a great way to put it.
Okay, next up, the compact derivative of the flagship, GPT-5 Mini from OpenAI.
GPT-5 Mini is all about making those top-tier generalist capabilities accessible. It's positioned to retain most of GPT-5's strengths. Advanced multimodal input, sophisticated function calling, best-in-class safety features, but with a dramatic speed and cost benefit.
What are the specs?
It offers a very respectable 400K context window. Pricing is highly competitive at 30.25 cents for input and $2 for output per million tokens.
And the speed?
Crucially, OpenAI reports it responds roughly 40% faster than the full GPT-5, and the fact that it scored 91.1% on AME 2025 shows it's retaining that high capability for complex, multi-step reasoning tasks.
So what OpenAI is saying is you maintain that GPT-5 quality, but at a speed and price point that makes it accessible for high-volume, real-time use cases, like advanced chat widgets or IDE assistants.
Exactly. And that output cost of $2 per million tokens, that represents roughly an 8x reduction compared to the estimated cost of the full GPT-5. So it's a very attractive, high-tier option, especially for customers who prioritize the ecosystem and safety features that come with OpenAI.
Then we have DeepSeek v3.2x, which seems to embody the open source movement's focus on architectural efficiency, even while offering a convenient API.
DeepSeek is one of the most technologically fascinating entries here. It's built on a technique called sparse attention.
Okay, sparse attention.
This architecture fundamentally changes how the model processes information, especially in long context situations. It intelligently prunes which tokens need to look at which other tokens. It's designed to be surgically efficient.
And the price point reflects that.
It does. Its API price is around $0.28 input and 0.84 output per million tokens with 128K context. The key takeaway here is that it matches the overall capabilities of its predecessor, v3.1, while providing huge efficiency improvements. It scored 89.3% on AME 2025. The architecture itself is doing the heavy lifting to deliver that price.
The fact that they can match performance with significantly lower compute cost is a huge validation for these optimization techniques over just sheer brute force. Okay, moving to Google, we have Gemini 2.5 Flash.
Gemini 2.5 Flash is really Google's high-throughput workhorse. It is specifically designed for speed and cost-effectiveness at massive scale.
And it's multimodal.
Right. It's a powerful hybrid reasoning model that supports advanced multimodal input, so it can process text, images, video, and audio, and it offers a substantial 1 million token context window.
And the cost?
Its API costs are $0.30 for input and $2.50 for output per million tokens. Google is positioning Flash as the model for high-velocity applications, for efficiency, and for high throughput. especially given its robust native multimodal capabilities, which are often required for tasks like inventory management or content moderation.
Finally, let's talk about Claude 3.5 Haiku from Anthropic. It's noticeably the most expensive model on this list, so why the price premium?
Haiku is the fastest Claude variant, and it's positioned a little differently. Anthropic focuses heavily on reliability, on strong instruction following, and on safety guardrails. That's their brand promise.
I see.
It offers around a 200K context window, and it sits at $0.80 input and $4 output per million tokens.
So they're betting that reliability is worth the premium.
They are. They're betting their instruction adherence is worth it. They actually claim Haiku surpasses the older, much larger Claude 3 Opus on many intelligence benchmarks, which again proves that optimization, not just size, is the key.
And who is that for?
For applications where ambiguity or hallucination is extremely costly, like legal drafting or regulatory summarization, users are willing to pay that 4x premium on the output because they're paying for predictability and reliability.
So even the highest priced model in this cost-effective list is still dramatically cheaper than the previous generation of frontier LLMs.
Oh, massively.
But beyond just the list prices, how are companies and developers achieving such huge cost savings on a day-to-day operational basis? What are the mechanisms they're actually using?
There are really three main strategies that developers and providers are leveraging in the backend. The first one is caching.
Caching.
This is huge for repeated workflows. Prompt caching, where identical or very similar inputs are stored and reused, it drastically reduces your cost because the model doesn't have to reread and reprocess all the setup instructions every time.
So, for example, if you're asking the same template question to 1,000 different receipts,
The prompt is only charged once. The input cost virtually disappears.
that's a phenomenal efficiency gain.
It is. Grok 4 Fast, for instance, offers cached input pricing at just 0.05 per million tokens. And Gemini Flash is even lower at 0.03 per million tokens. If you run repeated workflows, your total input cost can become negligible.
Okay, what about jobs that aren't real-time? Not everything needs a 2-second response.
That's where batching comes in. All the major providers, OpenAI, Google, Anthropic, they all offer asynchronous batch APIs.
So you can queue up jobs.
Exactly. You queue up non-real-time workloads, like maybe you're running overnight summaries or daily classification jobs. Because that computation can be amortized over a longer time window, it allows the provider to maximize their GPU utilization during off-peak hours.
And you get a discount for that.
A big one. You can often realize 50% cost reductions compared to making individual real-time API calls.
And the third mechanism, architectural efficiency, that seems tied directly to the performance breakthroughs we saw in models like Grok and DeepSeek.
It's the bedrock of this whole smart scale era. This involves techniques like mixture of experts or MoE and innovations like DeepSeek sparse attention.
Okay, can you quickly explain MoE for us?
Sure. With MoE, a massive model is broken down into many expert subnetworks. When you submit a query, the model's router only activates a small selection of those experts, maybe 2 or 3, to handle that specific task.
So the model is technically huge.
Hundreds of billions of parameters, potentially. But it's computationally sparse. That means you only pay computationally for the parts you actually use.
So the model is only firing the neurons it absolutely needs to process the request, which dramatically lowers the operational cost of every single query while still maintaining the breadth of the larger model.
Precisely. This is how they deliver frontier-level performance without the frontier-level price tag. MoE and sparse attention are why these models can handle vast contexts, like Grok's 2 million tokens or Quinn's 1 million, with far, far less computation than the dense models of the past.
So this cost-effective API frontier, where big tech is selling cheaper models, that's really only half the story, isn't it?
That's right.
Because at the same time, the open source community is just exploding, offering alternatives that prioritize transparency and total control alongside cost. Relying on proprietary APIs, even cheap ones, still means you're sacrificing control.
And that control factor is why open source LLMs are becoming imperative for forward-thinking businesses in 2025. The motivation goes way beyond just saving money on per-token pricing.
So what's the core driver?
First, there's the essential issue of transparency and accessibility. Open source models, where the source code and architecture are public, they just foster innovation. They allow developers worldwide to inspect, to customize, and to rapidly improve the models for all sorts of niche applications.
And for a business, that transparency directly translates into a huge strategic advantage, reduced vendor dependency.
Absolutely. Open source models are the key to achieving code transparency, deep customization, and breaking free from vendor dependency. If you own the model, you own the future of your AI stack.
You're not beholden to a single provider's sudden pricing changes.
Or worse, their decision to just deprecate a feature you rely on. You maintain complete sovereignty over your AI infrastructure.
Okay, let's dive into the standout players in this open source LLM renaissance of 2025. We have a list of 7 models, and what's really clear is that they are all hyper-specialized.
Yeah, they aren't trying to be generalists. They are targeting specific, high-value enterprise workflows.
Let's start with GLM 4.6.
GLM 4.6, which comes from the Chinese development community, is designed specifically for next-generation agentic workflows.
So multi-step tasks that require reasoning and decision-making.
Exactly. It significantly enhanced its agentic reasoning and coding capabilities compared to its predecessors. And crucially for those complex tasks, it features an expanded context window, going from 128K up to 200K tokens. That's essential for managing the long thought chains of an autonomous agent.
And how does it stack up?
Benchmarks show it clearly outperforms strong competitors like DeepSeek v3.1 on specific reasoning and coding tasks.
Okay, next we have GPT-ALS 120B. That GPT prefix suggests a collaboration that really shook the market.
This is a major market shaker. It's OpenAI's open-weight model release. It has 117 billion parameters, so it's positioned for production-grade, general-purpose use cases that need high-level reasoning.
But the incredible part seems to be its deployment efficiency.
That's the amazing part. Despite its size, it's designed to be deployable on a single 80 GB GPU.
Wait, hold on. 117 billion parameter model on a single GPU. How is that even possible?
It's all thanks to MXFP4 quantization of its mixture of experts' weights.
Can you break down MXFP4 quantization for us?
Sure, it's an extreme compression technique. MXFP4 is a highly compressed 4-bit format that's optimized for inference. Quantization essentially takes the full precision weights of the model, which might be 16-bit or 32-bit floating point numbers, and it compresses them way down to very small 4-bit integers.
And that shrinks the memory footprint.
Dramatically. It makes it viable for powerful, yet still accessible professional hardware. The model also offers configurable reasoning efforts. Low, medium, or high-SO developers can actively balance the depth of the response against latency and cost.
An open model from OpenAI with customizable reasoning, that really changes the calculation for a lot of developer teams.
It's a game changer.
Okay, what about Qwen 3 235B Instruct 2507? That name sounds enormous.
It is enormous, but it's also efficient, again using that MOE architecture. It's a flagship non-thinking MOE model, so it's designed for fast, deep retrieval and instruction following.
And the numbers.
It boasts a total of 235 billion parameters, but only 22 billion active parameters at any one time.
That sparsity is its magic.
It is. It stands out for state-of-the-art multilingual reasoning and features a massive context window of over 1 million tokens. This makes it a top-tier choice for massive document analysis, long-tail knowledge coverage, and open-ended multilingual tasks. You get huge performance without the computational cost of a dense model that size.
We mentioned DeepSeek's sparse attention earlier. How does DeepSeek R10528 compare as a pure open-source offering?
So DeepSeek R10528 is the open-source version of their reasoning-enhanced model. Its entire focus is on producing reliable, productivity-oriented outputs, especially in rigorous technical domains like software engineering and math.
So it's for when you need to be sure the answer is right.
Exactly. It achieved huge improvements in complex reasoning. We saw its accuracy jump to 87.5% on the AIME 2025 exam, which demonstrates its commitment to logic and truthfulness. This is the model you choose when reliability in technical contexts is absolutely paramount.
And we can't talk about efficiency without highlighting the champions built for the smallest possible footprint. April 1.5 Thinker is specifically focused on this.
April 1.5 from ServiceNow is an incredible showcase of intelligence density. It's a multimodal reasoning model, so it can interpret both text and images, and it delivers frontier-level results with only 15 billion parameters.
And the deployment.
The crucial point is that it's designed to run efficiently on a single GPU. It prioritizes practical in-house deployment for enterprise use cases while still achieving high AI scores. It just shows that 15 billion parameters, when architected smartly, is more than enough for complex commercial tasks.
That is incredibly low-friction deployment for a multimodal model. Now moving into agentic workflows, what about Kimi K2 and Llama 3.3 Nematron?
So Kimi K2 Instruct 09005 is another powerhouse MOE model with a staggering 1 trillion parameters in total, but only 32 billion activated at any moment.
Wow.
It's designed for incredibly long-term agentic encoding workflows, and it has a massive 256K context window. It's built for those complex, sprawling tasks where an agent needs to manage hundreds of steps and recall information across really long documents.
And the Llama 3.3 variant.
Llama 3.3 Nemotron Super 49B V1.5 is NVIDIA's optimized version of Meta's Llama 3.370B model. NVIDIA specifically tuned this variant for a highly efficient retrieval-augmented generation, or ARA, and tool-augmented chat, supporting long context workflows up to 128,000 tokens.
So it's the go-to for building internal knowledge assistants.
Exactly.
And finally, Mistral is a name that's just synonymous with lean, high-performing open models. What did Mistral Small 3.224B Instruct 2506 achieve?
This compact 24B model focused entirely on robustness in production. They achieved major gains in instruction adherence, meaning the model follows complex instructions really reliably, especially on difficult benchmarks like WildBench V2 and ArenaHard V2.
And what about for high-volume use cases?
Most critically, they successfully cut repetition errors, where the model loops or repeats previous phrases by nearly half, from 2.11% down to 1.29%. This makes it an extremely robust, predictable, and reliable choice for high-volume, real-time production deployments.
What really stands out here is that every single one of these open source models, whether it's huge or compact, is hyper-specialized in prioritizing these efficiency metrics. They are not chasing that generalist crown. They're aiming for competitive dominance in specific niches: agentic workflows, coding, long context, or multimodal tasks.
And this incredible open source ecosystem, coupled with the development of these smaller, smarter models, it all naturally leads us to the biggest strategic benefit for the enterprise, which is total control.
So the shift is strategic, moving from relying on external cloud APIs to local deployment.
Or what we now call privacy-first AI. This is where businesses can finally fully satisfy the requirements of complex data governance laws like GDPR and CCPA.
So how does local deployment solve that problem so definitively?
Well, it solves it by eliminating the problem entirely. Local deployment allows organizations to process sensitive data financial models, proprietary algorithms, patient data entirely within their own controlled, audited, and secure infrastructure.
The data never leaves.
It never leaves your physical or controlled virtual boundaries. This satisfies that privacy by design requirement mandated by regulations like GDPR Article 25, because you completely eliminate the risk of data transmission to or storage by any third-party provider.
So compliance becomes an architectural feature, not just a vendor promise.
That's a great way to put it.
And the benefits go beyond just compliance. We also talked about performance and predictability.
Absolutely. The performance gains are huge. Local deployment gives you predictable infrastructure costs because you've eliminated those unpredictable, variable per token API fees entirely.
And the speed.
Running these highly optimized models locally often yields sub-100 millisecond response times.
Sub 100 meters. And what's the typical cloud latency?
It often ranges between 200 and 500 milliseconds just due to network overhead, API processing, and queuing delays. For real-time applications like automated trading or instant customer service agents or code suggestions, local deployment is non-negotiable for both performance and predictability.
So we have these small, highly efficient models that we can run locally, but how do engineers actually take those models and make them truly punch above their weight on standard local hardware? This is where the optimization techniques come in. Let's start with quantization.
Quantization is really the backbone of SLM efficiency. Its role is simple: to dramatically reduce the model weights, the sheer file size and memory footprint, while retaining a very high degree of accuracy.
How does it work?
The process involves reducing the numerical precision of the weights from, say, high-precision 32-bit floating point numbers down to much smaller 4-bit or 8-bit integers. And it uses standardized formats like GGUF.
Okay, we need to pause on GGUF. What exactly is that?
GGUF stands for GGML Universal Format. It's essentially become the industry standard packaging format developed for efficient CPU and local GPU inference.
So it's like a zip file for models.
That's a good analogy. It's designed specifically to store the model weights, the metadata, and the vocabulary in a highly optimized way, which enables quick loading and running on consumer-grade hardware. Without GGUF and similar formats, local deployment just wouldn't be practical.
What's the real-world impact of that file reduction, say going from 32-bit down to 4-bit using GGUF?
It's transformative for deployment. For instance, the Q4KM quantization level has really emerged as the optimal balance for most enterprise applications.
And what does that give you?
This level typically offers 95% to 98% accuracy retention while achieving a massive 60% reduction in file size.
Wow.
So a 7 billion parameter model that might require 14 gigabytes of memory in full precision can be compressed down to about 4 to 5 gigabytes. This shift allows for deployment on hardware that's probably already sitting in your company servers, or even on an advanced consumer GPU like an RTX 4060.
Yeah.
It just dramatically lowers the barrier to entry for local AI.
Okay, so now the model is small and efficient. How do engineers tailor it specifically for a business process, like financial oversight or customer support? This is the model structuring process.
Right. This is the precise engineering workflow that brings that competitive advantage. It's really a three-step process. First, the engineer does selection. They choose a pre-trained, high-quality SLM, maybe an open-source model from a repository like Hugging Face that has a good baseline performance.
Yeah.
Second, they use knowledge distillation.
Knowledge distillation, that sounds intense. What's happening in that phase?
In distillation, they transfer the deep reasoning capabilities, the smarts, from a larger, more complex proprietary model, which is the teacher LLM, to the smaller, chosen SLM, the student.
So you're teaching the small model to think like the big one.
Exactly. This process trains the SLM to mimic the large model's high-level behavior on a specific task, not just raw facts. This allows the small model to skip that costly general-purpose training phase and instantly gain sophisticated reasoning abilities. It drastically reduces the time and complexity of getting it ready.
So the SLM becomes a Honda Civic that instantly inherited the driving skill of a Formula One driver.
That's a perfect analogy.
And the final step is where the specialization really happens.
Yes, the final and most crucial step is fine-tuning. They use optimization techniques like LoRa, or low-rank adaptation, to train the distilled model using a small, high-quality, domain-specific dataset.
Like a company's internal policy documents or specialized coding examples.
Or a library of fraud reports, exactly.
And LoRa is key here because it keeps that fine-tuning process affordable, right?
Absolutely. LoRa is an incredible optimization because it freezes the majority of the original model weights. It only introduces and trains a very small set of newly added parameters, these low-rank matrices.
So you're not retraining the whole thing.
Not at all. This means the fine-tuning process requires far less computational power, far less data, and it runs much, much faster than traditional retraining. This sharply increases accuracy and, critically, reduces hallucinations within that specific business domain, making the model a reliable internal expert.
So that combination of quantization, distillation, and LoRa makes that SLM a highly customized internal expert. But the final piece of the puzzle here is maximizing the throughput on that local hardware. We need to talk about VLLM, which seems to be the engine driving this high performance.
VLLM is often described as a game changer for on-premise inference serving. It's a highly optimized serving engine that significantly increases throughput. We've seen reports of up to 24 times faster inference in some benchmarks by intelligently managing the GPU resources.
And it does this through two key techniques.
Right. It addresses the fundamental memory bottlenecks of serving LLMs. The first and most important innovation is page attention.
Page attention. What's that?
Page attention addresses the massive memory fragmentation problem that's inherent in serving models that use a key value, or KV cache. Every token the model generates needs to store its key and value vectors in memory.
And in traditional systems, you have to pre-allocate a fixed amount of space for that.
Right, for the entire context history. And that often leads to huge wasted memory slots, especially with variable length inputs. Page attention solves this by dynamically managing that KV cache.
You compared this to operating system memory management before. Can you elaborate on that analogy?
Certainly. Think of how your computer's hard drive uses virtual memory pages. Page detention breaks the KV cache into small, fixed-size blocks, and it allocates them dynamically as needed, rather than reserving one huge, continuous chunk of memory.
So it's more flexible.
Much more. When a sequence runs out of blocks, the system simply allocates a new, non-contiguous block. This dynamic allocation eliminates fragmentation and dramatically increases the effective memory capacity of the GPU, which allows it to handle many more concurrent users or much longer sequences.
And the second key technique is continuous batching, which is all about maximizing GPU utilization.
Right. Continuous batching maximizes efficiency by processing requests immediately as they arrive, rather than forcing the system to wait for a full batch of requests to accumulate before processing begins.
So no more idle time for the GPU.
Exactly. As soon as one request finishes, the GPU immediately starts processing the next pending request in the queue. This is crucial for maximizing GPU utilization, especially in high traffic scenarios, and allows the system to handle a substantial workload without the prohibitive costs of less efficient methods.
So this combination of SLMs, GGUF quantization, LoRa fine-tuning, and VLLM optimization is really what allows companies like IBM to launch models specifically built for this new era. Tell us about the Granite models.
IBM's Granite models are a prime example of the smart scale era in action. They're a family of open, performant, and trusted AI models built explicitly for business use.
And they come in different sizes.
They do. They offer small models across various sizes, nano, micro, tiny, and small all, optimized for core enterprise workloads like retrieval augmented generation, agentic workflows, and internal guardrails.
And the key features.
A staggering 70% or more reduction in memory requirements and 2x faster inferencing speeds compared to their general-purpose counterparts.
And there's that incredible case study that proves the financial impact of this focused, efficient strategy.
It's the perfect illustration of intelligence density triumphing over sheer size. A large financial company implemented the Granite 7B lab model for a very specific task: Q&A over reconciliation procedures.
The crucial, high-volume but very repetitive process.
Exactly. By using this smaller domain-tuned model running internally rather than relying on an external proprietary behemoth, they achieved AI support that was 95.7% cheaper compared to using GPT-4 Turbo.
Wait, 95.7% cheaper? That's almost 100% cost reduction. It means that the AI functionality essentially went from being a high-cost operational expense to an almost negligible utility cost.
That's right.
That completely changes the ROI calculus for any internal AI project.
It makes previously marginal AI projects immediately viable. If you can perform millions of reconciliation queries at that price point, you unlock massive competitive advantage and productivity gains. And we're also seeing companies like Liquid AI pushing the limits even further, aiming for the edge with their Liquid Foundation models.
Oh.
Right. These are models inspired by biological neural networks, and they're designed for edge-native deployment. They're promising to deliver the fastest AI with zero cloud dependencies, making privacy and sub-100 meters latency available even on the smallest of these powerful devices.
This shift isn't just theoretical, then. It's rapidly transforming how businesses operate across the board. Let's look at where these cost-effective SLMs and low-cost APIs are actually being applied today, starting with high-volume enterprise applications.
High-volume, high-repetition tasks are exactly where these cost savings truly shine. Let's take financial oversight.
Okay.
Companies process hundreds, if not thousands, of documents like receipts, invoices, or contracts every single day. They can use an SLM, highly tuned with LoRa, operating with fixed, defined prompts like, what is the purchase amount, or who is the seller, to automate high-precision data extraction from those diverse documents. It's a repetitive task where the SLM's speed and precision, running privately, vastly outperforms a large generalist LLM because it's tailored to the exact document format.
And for high-traffic environments, like web portals, customer support must be a massive beneficiary of the Flash models.
Absolutely. For high-traffic chat widgets and real-time analytics, you need models built for speed and burst capacity. Models like Gemini 2.5 Flash and Claude 3.5 Haiku are specifically designed for high-throughput interaction.
So they can handle spikes in traffic.
They can manage thousands of concurrent requests at an incredibly low marginal cost, ensuring immediate and accurate responses that are consistent with the brand's voice, which is something expensive, slower cloud-based options might struggle with during sudden traffic spikes.
And for software development teams, code assistance is a core daily workflow that requires extremely low latency.
GPT-5 Mini and Mistral Small are now essential here. They provide accurate, low-latency code suggestions, completions, and refactoring advice, and they accelerate development workflows dramatically.
And the cost is no longer a barrier.
Exactly. The fact that the token costs for these high-quality models have dropped so dramatically means developers can integrate them deeply into their IDEs and just use them continuously throughout the day without management worrying about some astronomical cloud bill at the end of the month.
The final high-volume application you mentioned involves risk analysis in banking and finance, which touches back on that need for absolute privacy.
For critical tasks like fraud detection, anti-money laundering monitoring, and credit scoring, instant predictions are non-negotiable. But the data must remain internal due to rigorous compliance requirements.
So you run an SLM locally.
Highly efficient SLMs are run entirely privately within the organization's internal system to ensure immediate predictions in milliseconds. without any data transfer to external APIs. This guarantees both compliance and instant insights that can save millions in losses.
And beyond pure text, these optimized models are also expanding into other modalities like vision, audio, and video, making them capable of handling the messy, real-world data that businesses encounter.
The development of multimodal reasoning in SLMs is critical for operational efficiency. Take April 1.5 15B Thinker and Gemini 2.5 Flash. They support both text and image input.
What kind of tasks does that enable?
It enables complex real-world tasks, like the courier company use case we analyzed, where they're monitoring package integrity. The AI compares images captured at multiple distribution stages, say loading dock, transit hub, delivery van, to detect damage. It provides high-level visual analysis done on an efficient, localized budget.
And the audio revolution is being powered by platforms like 11 Labs, which are pushing the boundaries of expressive speech.
11 Labs is the uncontested leader in expressive AI voice. Their 11v3 model provides incredibly lifelike, emotionally rich, and expressive speech for creators and enterprises, and it supports over 29 languages.
So it's not just about the words, but the delivery.
It's about nuance and feeling. And crucially, they also offer extremely low latency variants like Flash v2.5, which achieves 75 millisecond latency for conversational use cases. That makes it a viable alternative to human voice agents.
And it's seeing major adoption.
The fact that major figures, including the actor Matthew McConaughey, are investors just illustrates the widespread adoption and trust in lifelike AI audio across media and enterprise.
And finally, we're seeing AI video generation move from being a niche novelty to an absolutely essential business tool with platforms like Synthesia.
Synthesia, which is trusted by over 90% of Fortune 100 companies, is transforming business training and internal communications globally.
In what way?
Instead of spending weeks on filming, editing, and translating training videos, companies use Synthesia to create professional, personalized video content, complete with AI avatars and text-to-speech in minutes.
That's a massive efficiency gain.
It is. This allows large companies to quickly update thousands of courses or translate 100 hours of content into dozens of languages in minutes, rather than days or weeks, making corporate training scalable, adaptive, and geographically agnostic.
This has been a fascinating deep dive into the changing AI landscape. If we zoom out, what is the single biggest synthesis point here? Is it that it's no longer about how big the model is, but how smart the architecture is? The triumph of intelligence density.
Precisely. The frontier of AI is now defined by that crucial ratio: performance per parameter and cost. The rapid availability of aggressively low-cost API models like GPT-5 Mini and Grok 4 Fast, coupled with these highly optimized open-source models like DeepSeek GLM and IBM's Granite family, it's making frontier-level capabilities accessible to everyone.
And that's fundamentally shifting the economics of deployment away from those centralized giants.
It is.
This cost destruction is the ultimate accelerator of innovation. Startups, academic labs, high-volume enterprise workloads that were previously priced out are now viable. The cost barrier to entry for top-tier AI capability is just rapidly crumbling.
When you can run a 7B model locally that is 95% cheaper than a cloud LLM for your specific task, you start seeing mass adoption. And that undeniable trend leads to the final provocative thought for you to consider. If inference cost is quickly becoming a solved problem due to all these architectural innovations, sparse attention, quantization, VLLM, then the next major competitive battleground won't be in raw model intelligence.
So where will it be?
It will pivot entirely towards security, governance, and control. So what does it mean for your organization when the cost of AI is almost negligible, but the demand for data control for building secure, privacy-first, and easily governed hybrid AI systems leveraging these powerful SLMs is absolute?
Control, not cost. That's the future of enterprise AI deployment.
That's it for this edition of The Deep Dive.
Thanks for joining us.
We'll catch you next time.